All right, thanks everybody for coming today. I really appreciate it. My name's Nate Slater. I'm a solution architect at Amazon Web Services. I work in the San Francisco Bay Area. And today I'm really happy to introduce Kuldeep from Expedia, who is going to be talking about how Expedia has delivered microservices using the ECS service. And with that, I'll turn it over.
Thanks, Nate. Hi everyone, I'm Kuldeep Chauhan. I'm a principal engineer at Expedia. I work in the cloud platform team predominantly in Expedia. I have been working in the cloud space for about 4 years now. Prior to working at Expedia, I worked at Shell Oil and Gas, and before that I was at Microsoft as well. I'm here to talk about two things. One, how do we enable teams to go and deploy to AWS? We built a platform as a service internal tool that's a wrapper around how people can provision the boxes in AWS and then how they can go and deploy. My talk is the tool can do so many other things, right, than just ECS. My focus of this particular talk is around ECS. So the second thing that I'm going to talk about is how we actually manage the clusters, the ECS clusters. With that, as I said, I'm from Expedia. Expedia is one of the world's largest travel companies. And if you don't know what Expedia is, I'm pretty sure most of you already know. You are missing out on a lot of deals and travel packages. So as you can see, it's a big brand. We do have a lot of travel sites under the same umbrella. And we have about more than 100 points of sale across 60 different countries. So that's how big our site is. And we are passionate about travel, and we want to make sure all of our customers and partners also have a great travel experience. With that, I wanted to show how our current AWS infrastructure looks like. So we do have our own data centers. So you can see mostly it is in US. But our presence is across the globe right now. Not everything, but there are a few pieces of our site that's deployed across different regions. And that arrows are just to do a representation that it's a mesh network, that everything connects to each other, and everything also connects back to our data center that we have in US. We do use a lot of AWS services, but I'm going to focus on primarily ECS, load balancers, and a little bit Route 53. So as I mentioned about ECS, we are running ECS in production. We have more than 200 microservices that are running in AWS. This is just our production cluster visualization. So one of the tools that you can see, there is a link in the bottom. We built this tool called as C3 Ways, and we open sourced it. It can be used for any of the ECS clusters out there. And we do use it a lot to see how our clusters are performing. So you can see that it's we have about 5 different regions where we run our clusters. And this is only some of them. That's the reason you don't see all the 200 microservices that I mentioned. Our clusters are across different regions as well. We do have different environments. We have our test environment. We have our different production environments. And then we have our the staging environment as well. So ECS is used widely. This is just showing our production usage. So as I mentioned, I'm going to talk about what we built for teams to go and deploy to AWS. Our journey started close to 4 years ago when we wanted to go and try to see if we can deploy to AWS of our services that we have. And we picked one of our services. That was also a brand new service that was picked. And then we invested into Chef to do our deployment automation, and then we treated everything that we deployed as infrastructure as a code. So there are a lot of APIs that Amazon provides you, right? So we define our subnets, what subnets to use, what security groups to use, and then we also do auto scaling with traditional CloudFormation stacks as well. And for that also, we have configuration information to say how many instances do you want as the minimum, how many do you want as maximum. So we built a lot of tools across this last 3 years. So it has evolved over a period, and then by 2014 of May 2014, we had only like 12 microservices, if you will, deployed to production. Because there were so many things that teams have to do before they can start deploying into AWS. One, to use our internal microservice architecture. So we have a lot of libraries that we build for teams to use. So they have to use those, like basically understand how to wire them up. Then write a chef cookbook, write all these files that I mentioned, like the infrastructure config file and then the deployment config file. And once those two are there, then they have to check it in and then figure out. Basically, we did have automation to create one instance or a stack, but it was not auto-scaling enabled and all this stuff. So there was a barrier to entry, right? So there are people who need to do some work. But it is the same work that everyone has to do. It's nothing different. There are a few things that are different, of course, but most of those things that I talked are almost the same. So what we did in 2014, we built a tool called as Primer. We called it as Primer internally. It's a tool that bootstraps all these things that I mentioned right now for teams to go and deploy to AWS. All they have to go is basically go and enter a few things, saying, I have a demo as well. I'm going to do a live demo. Is to go and enter a few details, tell what is the app, the microservice name, and then some of their contact details, like what is the app team name, where do I send HipChat notifications to, what email to send notifications. It does few things, but we started only with Spring MVC, Tomcat-based applications. That's what we started. Right now we have about 26 different types of templates that have been built around them, all as an open source model. There is nothing that there is not one team that controls who can build these templates. Teams can make those changes, issue a pull request, and then those gets available in Primer. Again, the same thing as I mentioned, there are different types that we support. This is an internal dashboard that we are building to have this information available. It's in a transition mode. I'll show you the existing one, but this is the new one that we are building. To go a little bit into the Primer architecture, as I mentioned, someone goes to a web page, says, hey, I want a new app, right? And then the app goes and creates a GitHub repo. We use GitHub Enterprise, which is behind our firewall. And then there is a template project that we use. Like, let's say, as I said, Tomcat has a template project, Spring Boot has a template project, Drop Wizard has a template project. And then once we do that, we create a Docker file for them, once generating the template repo, create the Docker file, and then check them in. And we use Jenkins for our CI/CD. So what we do is automatically create them 2 different jobs. Earlier, they had to contact someone to say, hey, can you create me a job? Or there was a self-service portal as well. But most of the times, it is the same thing that people have to do. It's nothing different. Either run Maven clean install, or if it is Node, it is npm install. So that's also automated for them. And then we use Splunk for our log management. We automatically create them configs, like whatever is the input conf that you need to use, what log file to look for. So that's also done for them for free. And then we push our metrics to Graphite. We use Grafana for visualization. So we automatically create them. There are a few libraries that have been built to send let's say for Java, right? Send all the JMX counters automatically to Graphite. And then the notifications, we use HipChat a lot. Of course, email is still there. There are some teams who use Slack as well. So this is what Primer, the first part was creation of the app, right? Someone went to a page, they created an app, that's what they got a Git repo right now. So typically what happens is after you enter, within 7 minutes, you get an email saying that, hey, your app is ready for development. So basically you can clone the repo locally and start making your changes. So this is what happens after the fact, right? Like you make a change in your repo, you push it to GitHub again. Once you push it back, then we use the GitHub webhooks. There is a GitHub webhook that triggers the job. Then we use the Jenkins plugin for a Docker build. Nothing fancy there. There were some issues with that plugin. We issued pull request as well to do retries. But the basic Docker plugin out there, use that to build the Docker image and then push it to a private registry that we have. And then that calls another job, which actually goes and deploys. All of the philosophy, most of these jobs are the same job that everyone uses in Jenkins for deployment. There's nothing, not everyone has a different deploy job, right? Those are all controlled by parameters. It's just, you tell what version you want to deploy, you tell the app name, and then what region you want to go and deploy, and then the deploy job takes care of it. And on top of ECS, we wrote our own Ruby scripts. So that is calling a Ruby script that's a wrapper around ECS. So it goes and creates task definitions in ECS. It creates a service in ECS. It creates a load balancer. And then it says how many tasks you want, and then it wires up all of them. And we heavily use Route 53. So every app gets a Route 53 CNAME when it gets created. And then the way that we send different notifications is, and we have been following this serverless architecture for a while now. So when the deploy happens, that Ruby script actually sends a notification to SNS saying that we actually send multiple notifications, not just sending a deploy succeeded or something succeeded. We actually send every individual piece as well. Someday you could do something with it, right? So we have lambdas which are listening on that SNS topic, and they look for different types of events that we send. So one of them being here, sending it to email, so that it sends to email. There is a lambda that's listening for HipChat, so it sends it. And we have another tool, I'll save it for another presentation, that actually gathers all these metrics and shows how many deploys did we do over a period of time. There are a lot of other details that it shows. But this is very high level. This is what our ECS platform does. And as I mentioned earlier, right, we have our own registry. This is the Docker trusted registry. We hosted it in AWS. And then when I walk through the demo, this will come into picture. But there is a structure that we follow, the same thing, right? Like you have a node Docker image that you have, and then you define what you want to define. So we created base Docker images for each type of app type. It says Spring Boot has one, Node.js has one, so and so. Actually, maybe this one. Right, so this is a simple Node.js one that we built, right? This is the base Docker image that everyone uses, at least all the Node.js apps. The first one, as you can see, it is just getting it from the open source Node 6.2.1. And then we add few things to it, like you can see dumb init and most of our deployment. And every Docker image has its own type of Docker image, has its own entry point.sh file, which says how to run it. For if it is Java, it has a Java command line. If it's Node, it has an npm command or forever command. With that, I'll switch to a demo mode and hope that the demo goes fine. Let's see. Still on network. So I went to the portal. The very first thing that I get is asking me what is the app name. I'm just going to put AWS Summit here. Team name, we call it as Stratus, our internal cloud engineering team. going to put my email. I'll leave it as default. There is a default room where it is going. It is an optional field. And then this is where, as I mentioned, these are the different types of template types that we support. As you can see, the list goes on, and there is a new type that gets added. I'm going to do the first one, the Web MVC. And as we are transitioning from a CloudFormation deployments to Docker, there are a lot of things that teams have to understand how Docker works, right? Like, it's not always that you have a resource to go and figure out what's going wrong with it and whatnot. So when someone selects a type of primer app that's supported by ECS, we give them a page where they can go and look for Docker guidelines, basically. It talks about what is like basically scaling your application horizontally. So there are a few guidelines that we put together. And this is all for internal tracking. This is to visualize who is spending what inside the company. So that's all it is. Okay, so yeah, it's going to take about 7 minutes. In the meantime, I will walk through a few things that I wanted to show. So as you can see, the repo doesn't exist at this point because Primer hasn't gotten at that point to create the Primer repo. It is just, again, plain old Jenkins here. And this is the one that I mentioned earlier about the tool, which is open source. People can look at it, and you can use it for your ECS cluster management. Okay. When I want it to be faster, it's not. Okay. So most of our chef cookbooks and all this AWS infrastructure that we have is in public GitHub, which is again a private repo that we have. But everything else, all our source code, everything, it actually resides inside our firewall. So as I mentioned, we create a file for every type of app that gets created, and we do it today with like per zone as well. And you can see there is this particular file that talks about few things like what subnet to use and different types of instance types. But again, this is not that much relevant in a Docker infrastructure, right? So Docker, I don't have a concept of a subnet. I don't have a concept of security groups. That's at the cluster manager level. I'll log into my AWS portal. So Primer already created the repo by now. Again, it's empty. There isn't much anything in it. By the time it completes the creation, it will have more stuff there. And I'll just log in this in the meantime. As I mentioned earlier, we have our own repo where we create all these base Docker images. For example, the one that I showed you earlier was Node.js one. And you can see that this one basically talks about the same file that I showed you, right? But for an application, when you see for an application that's using this, all they have is just one line here, right? There isn't much anything here apart from this one line, because they don't have to, again, create, like download from Node or do dump init into it or run forever. We automatically take care of it for them. If people want to override this, they are more than happy to override, but they don't have to, typically. So similarly, we have for different types of app that we support. And again, not every type that we support through Primer currently has that support. But there are few that we do today. Okay, let me refresh this. Yeah, so you can see that it's creating these files. So let's go back here. So as I mentioned, something is not done. Okay, it hasn't checked in yet, so that's why. We should have started this before. So as we go to ECS that I mentioned earlier, this is our test environment. Our test environment predominantly is in Oregon, and as you can see, there are different clusters that we are running, and the biggest one being the test one here, where we have about 37 actual ECS hosts running behind the scenes, and we do have about 400 tasks running under it. Right? So it looks like there is a deployment that's happening at this point. It's good. That's the reason it shows as one pending task. Let's see if I can come back to my. Right, so this is where it creates some of the infrastructure that we need, saying how many number of instances do you want, what is the minimum, what is the maximum, what regions can we go and deploy our ECS task to be. So this test environment, so you will see usually one zone, but all our production deployments are multi-AZ. It's like not one AZ. This is just our test environment. And I think I had these. So this, as I mentioned earlier, right, this is what we use for sending our notifications. How many of you have already used ECS? If you are already familiar with it, you might know this. By default, you don't have to provide how much CPU you want, how much memory you want, but most of the times, what happens is if you don't do it, you get whatever is left on the box. But when you have 20 containers running on the box, and let's say some service uses all the CPU, so all the other containers get affected. So what we do is, every app that gets created by default microservice, it gets half CPU and then 1.5 GB of memory. And what we do here is, this is someone said, hey, I don't want the defaults, but I do want something else. So this is what this particular app needs. But that's how people can customize what they really want. And if I switch back. Yeah, as you can see, this is all done for the application. So I'll come back to this later once the app gets created and everything is deployed. But in the meantime, I will go over the Docker, the cluster management, how we actually do cluster management with ECS, and what are the issues that we ran into. So this is how our base image looks like for the Docker ECS host that I showed you earlier. Right? Those were 37 of those. So this is basically what gets added. So you have a Amazon base AMI that's ECS optimized, and then on top of it, we add these things to it. So we do our OS hardening. There is a OS hardening script that we have that we go and run on the ECS optimized AMI. And there are some security configurations that we do, network configurations, how we want them to be. And then log forwarding for the base instances. I'll talk about that later on as we go. And then we use cAdvisor for the container level monitoring. And then Docker cleanup to clean up the images that are not used. So cAdvisor gives us the cluster level, the instance level monitoring from Google. We use that. We don't use Hipster. We have cAdvisor on each host if you want to go and look more on the same box. And we do combine that with Grafana. So Grafana has a plugin to get the data from, from CAdvisor, we push it to InfluxDB. And from that, we use Grafana to visualize that data as well. So I'll talk about how we do our cluster upgrades. For most of you who are already have used CloudFormation and auto-scaling groups, if you haven't customized much with the update policy, or if you even have tried updating CloudFormation update, it typically goes and updates the whole stack once, right? Like there is no concept of doing one box at a time. So the initial version on how we actually used to do our cluster upgrades, cluster management, was that we had a stack created using CloudFormation with auto-scaling so that the actual ECS host instances can scale up and down based on CPU reservation and memory reservation. And then there was some config information that I mentioned earlier, right? Let's say I changed some OS hardening script, let's say. Like there's some other setting that I need to do. We used to use user data on the actual instance. Then we used to apply that. So it's all good when you want to do an update on this. So what updating this actually does, it goes and updates, let's say there are 20 boxes, it goes and updates all 20 at once. It doesn't do one box at a time. So we ran into some issues with that approach. I'll talk about that when I talk about the lessons learned. But this is the current approach that we do today for our zero-downtime instance replacement. So let's say a new ECS AMI comes out, or something that we need to upgrade, right? Like there is, or at least there is a ECS new AMI or an agent or something else that, or Docker version as well. So this is how the stack actually looks like when we are about to do this. So the very first thing that happens, and what we do with this is we no longer do an update. The update concept has been totally taken out. We just do a replace instance. There's always a new instance that comes out, even for a small user data change as well. So a new instance comes online, and then auto-scaling groups starts terminating that instance, right? So what we do is we use AWS Lambda, and then we change something on the auto-scaling group to say, do it, wait on the terminating state. So it's basically terminate waiting rather than actually terminating. So it actually waits until 30 minutes before it gets terminated. What it does for us is it allows the, and after doing that, we actually issue a command to ECS saying that this instance, deregister it from ECS. Once we do that, as I said, we wait 30 minutes. So 30 minutes is a lot of time. I'll explain why 30 minutes is a lot of time, but this gives us the option for ECS to move those tasks to a different instance, right? It's not guaranteed that that task will go onto the new instance that we created. It could be any of the other remaining tasks. So as you can see, example here, it goes to the second two, the third and fourth one. And then a new instance comes, same approach, right? The old instance gets terminated, and then the task may get onto, all of them get onto the new one, and they can go into the old one as well. So this cycle repeats, right? So we slowly repeat this, and then there's a new instance that's coming up, and then again it's sending those updates. Same process goes on, right? So at this point, we have all the tasks that have been moved onto the new one. So the old one is still there. The old instances are there, but the tasks have already been moved away. So then we slowly start terminating the instances actually, and then slowly all our stacks move away. Right? There are downsides, right? Like we have to wait 30 minutes for a cluster upgrade to happen, but this saves us with our production outage. We had a production outage running ECS, doing an update to our cluster ECS cluster upgrade. We have about like 5 minutes downtime for our applications, and we want to avoid that when we do this cluster upgrade. Again, ECS takes care of running the cluster for you, right? You don't have to do anything. Right? Amazon will take care of you. But there is always an operational cost associated with running these things. That is where we are investing a lot of our time to figure out how we do upgrades and whatnot. Like the master and the slave workers, all that stuff, Amazon takes care, but this is where you manage your cluster itself. And then how we detect the broken instances, right? There have been issues for us where we had either Docker timing out when we do a Docker PS, or Docker was not able to even pull up images from the registry that I showed earlier. There were multiple reasons for it, but we also want to do it as a proactive monitoring rather than being reactive. So what we do, again, it's not fully automated yet, but this is where we basically we look for these commands that I mentioned here, Docker images and Docker PS, and then we send that data to CloudWatch. And then using CloudWatch, we create an alarm, and then that alarm sends, we get an email to our team. And I think we also look for if ECS agent is running. Once that email comes, right now, we have a script that we run. The next step is to fully automate it. We look at it, and if it is a known issue that we already know, and if there is a small fix that we can do, we do it. If not, we actually run the script evict instance. Basically, it is taking out from auto-scaling group using the same concept that I mentioned earlier, is Lambda, but we run it from our local laptops, and that takes care of it. How do we analyze cluster-wide issues? Again, there are logs on the disk that CloudFormation generates, that ECS generates. We pipe them into Splunk, so we use Splunk heavily. And as you can see, and then we can query for different states, whatever state. This is where it couldn't transition for some reason, but you get the feeling, right? Like you can query for anything that you want that is generated part of the log. The actual ECS host instances that I showed earlier, they scale up and down right now. I mean, the auto-scaling support at the task level was introduced only recently in ECS, but this is at the host level. So we scale up based on the CPU reservations, and as I mentioned earlier, we actually reserve every app, a particular CPU, a particular memory. We don't create any task definition without anything reserved. So we already know how much we are going to use. So we scale up and scale down. There are some downsides that we had with this OR condition when we are doing scale down. I'll talk about it when I talk about the lessons learned. But we scale most of the time at the memory, because most of the times apps go very high on asking they want more memory than more CPU. We use C3 4 extra large as our base instance type. We found that it has the right balance between the CPU and memory, and was also cost effective. So that's the instance type that we use for most of our ECS hosts. So I talked about how we do these things, but now I wanted to mention what did we learn with how we were using ECS. As I mentioned, Docker, CloudFormation and auto-scaling group are two different services. They are not the same service, right? Like you issue a update, CloudFormation can go and update all the instances that are behind that the stack, or you can run CloudFormation and then auto-scaling is doing something else. So there is not a lot of communication between them. There is, but there are a few things that are still missing. Here, the first one, as I mentioned, use immutable servers with CloudFormation. Earlier, we used to do an update of the existing instance. I think version maybe 6 months ago or maybe 4 months ago, there was a new version of ECS image that came out that attached a EBS volume. So there were 2 EBS volumes rather than being 1 EBS volume. And the Docker was, the change was to have that Docker run on the second EBS volume than on the first one. So we typically went ahead and doing a Docker, the CloudFormation update. What happened was, as I mentioned, it runs across the board. So it updated it across the board. But with the change that was introduced with this ECS AMI update, it means that there is a downtime associated when it is doing an update. So we all across the cluster, we were down. So it was about 5 minutes before we recovered. So that's the reason we changed it completely. There is no more an update. Even for a small change, we just do an replace instance. The other one is, so as you are already aware, we mentioned CloudFormation and auto-scaling group go hand in hand for us. There was about, I think, 4 or 5 months ago, it was multi-AZ support that was added to ECS. And we started to enable that at our auto-scaling group level for our for actual instances as well. Because at that point, we were just doing one. But later on, as ECS was also supporting multi-AZ, we started to support multi-AZ at our container instances as well. So as auto-scaling saw that there was 2 AZs that it needs to go and operate on, it tried to go and spin up the new boxes on the new AZs and try to rebalance it. CloudFormation update policy did not have something, the AZ rebalance. So what happened was auto-scaling just timed out because, CloudFormation just timed out because it was taking more time for auto-scaling to spin up new boxes on the new AZ and then rebalance it. So which basically caused CloudFormation went back into a rollback mode, and then then we had to talk to the AWS support to understand what happened, and then we went back. So what we do is, when we do a CloudFormation update, make sure you understand all the policies that you want. As the update policy, there is an update policy that you can define when you do a CloudFormation update. What we did in this particular case was to do we basically suspend CloudFormation whenever it is doing a AZ rebalance. So that way, CloudFormation is actually literally waiting until auto-scaling says, hey, I'm done with my AZ rebalance, or even the CloudFormation saying I'm done. So that's what we did. And the other one was the scaling down. As I mentioned earlier, we scale up very efficiently, but most of the time what happens is we scale up too fast when someone asks more memory, but the scale down policy said if the CPU is less, then you also scale down. So what happened was we scaled up on one hand, but we scaled down as well on the other hand because of the CPU. So be very careful on what type of policies that you define. Most of the times it could be an AND situation rather than an OR situation. And I think the other one that this is the ones that I had, what we are planning to add at the cluster management level is to basically add auto-scaling support at the task level. We don't have it at this point. We are planning to add that soon to our automation. And then instead of spinning one instance at a time, you can actually spin up, let's say if there are 6 instances in the cluster, you basically go and create 6 more instances, and then deregister the existing one so that all of them move to the new cluster, and then you can delete them at once. So that's something that we are planning to do. And ECS doesn't have a concept of a profile. So you have a EC2 instance as a small, large, medium, extra large, right? Because most of the times, as I showed earlier, there was a different CPU, it's a different memory that people can define. But we are planning to support actually like a workload profile so that our teams, the microservice can tell us what type they want, whether it's a medium, large, and we determine where to place them. So we could have a different cluster for different workload profiles so that everyone doesn't have to work in the same profile, the same cluster that we have. And again, right now we are not at a point where we can treat clusters as cattle, right? It's some amount of effort that we are putting and they are waiting. So we want to be a place where we can just delete the whole cluster and still be able to run our infrastructure. So with this, I'll go back to my demo presentation, hopefully it completed. right? So as I mentioned earlier, it created a job for the same service. And not only it created a job, it actually created a Docker image, and it pushed, so it did a Maven clean install, basically, right? They have a war file that was created locally, and then we did a Docker push to our registry, and the Docker image at this point is available for us to use. Right, so this is the Docker image that we pushed, and you can see the tag that was showed here as well, the same tag. Like we follow git sha, like there is no file that where we put all versions. Git sha is our version, so whatever is the git sha version, that's the same version that we use. And same, the 561 is the same version that you can see that was pushed to Docker registry as well. And that's good. Now let's see if I can. So this is the job that I mentioned. So once this job completes, once it has actually pushed the image to our Docker registry, this actually also calls our deployment jobs. So this is our deployment job for our test environment. Looks like it already completed, right? So it took about 3 minutes. You could ask me, why did it take 3 minutes? Docker doesn't it should start in like few seconds rather than taking minutes? One of the drawbacks that I see, at least in this, in the cluster managers and whatnot even, is there is no concept of a blue-green deployments, if you will, where you want to deploy a new version of your service, microservice, be able to do some kind of a testing before you actually make it live. ECS does provide you the option to say, hey, I have a new version, you apply that change, and then ECS will take care upgrading the containers to the new version. The problem is there is no way that you can actually test the new version before it actually goes. What we do is we create a canary service. So for every service that we, maybe I'll just show it. So example. So this is the task definition that I created. I did not write a single line of code for this one. As a developer, I did not write anything. The platform took care of it for them, right? So it created this. And for Splunk logging, we follow a sidecar approach. So when we create the task definition, not only just we create the application related container, we also add one more to it, a Splunk container as well. And we mount our volumes from the base container out to the Splunk container, so that Splunk can forward the logs to the indexers that we have. If I go back, all right, so the same thing as I mentioned. So our automation went ahead and what happened here? I have to search. But anyways, so the app got deployed, so something I'm missing. Yeah, so as I mentioned, we create a canary stack so people can actually do some testing for them before they actually roll it forward. So they can always do a test, and then once the test succeeds, they can do a perform. So what we did about like 2 years ago was to actually decouple deploy and release. So you can deploy as many number of times you want in the day, but you have to do an explicit action to say, I want to take traffic. So that's what we call it as release. So as part of, that's where we do this, our blue-green deploys, where the deploy phase creates a canary stack for them, where if they have some kind of automation that they want to hit this endpoint, they can hit that endpoint and do their testing. Once it works, then they can do a release. The release is where it goes and actually updates the existing, the new stack. Right, so as I mentioned, it is a Spring MVC app. We have our internal microservice libraries. We call them as E3 Prime. This page basically talks about how to use them because that has been already wired in. I'm not sure why the endpoint actually did not come out. Yeah. So sometimes it does take time for us. We use heavily Route 53. Sometimes it does take for the Route 53 to be propagated on our DNS servers. But as you can see, this is the same approach. And what we do once this is done, we actually go and update, call an update to ECS, saying this for this service, looks like. Right, so this is the service that was all automatically created as well, and it does talk about the number of instances that it wants and the load balancer integration that we have. One of the things that I also want to call out is at this point, load balancer, because of how it is a static port that you need to define, we actually maintain a list saying that this app gets 10 ports, and then we are hoping for the to do a dynamic port mapping later on. But at this point, because load balancer only supports a static port, you always have to have a port that says this service is running this port on this box. And then that's what we expose it to the host instance. Okay. And as I mentioned, we also send logs to our Splunk infrastructure, and we also send metrics to Graphite infrastructure that we have. So that's the reason why it takes that 3 or 4 minutes. It's not that we can't run the cluster, do an update in minutes, right? So there are few aspects that are involved, and as you can see, this is our job that's used heavily, that deploys all of our services. And you can see this job has been run 26,000 times. So it's heavily used. And it takes about 3 minutes. Every check-in that you make going forward to that repo, you actually get deployed. So I think maybe I just show this. So this is the repo that got created, which actually has the source code right now. Earlier, it did not have anything. Now it actually has the source code. And if you look the Docker file, it's just like 2 lines, right? One, use our base AMI, base Docker image that we created for Tomcat apps, and then copy the war file to it. And we do a lot of other like on-build commands that Docker provides. So there are some of the on-builds that are there in the actual Docker image as well. So I think that's all that I had. I'm here for any questions. So, but that's pretty much it. I will be here if you have any questions, if you want to ask me around. I think we do have time if you want to come and use the mic.